Okay, well, let's continue our work on chapter 5 that we were talking about light. This is part 2. So there are things that we usually refer to as the chemical fingerprint. So each type of atom has a unique set of energy levels, okay? So these energy levels could be an electron that's cascading back to a lower energy level. This could be a rotational energy level. This could be vibrational energy level. Each transitions correspond to a unique photon. So for example, if you have from level 5 energy going all the way to level 3, then you're getting a specific energy being emitted out of the atom, but then that energy has this wavelength, okay? So if we know exactly this wavelength, we can know exactly what molecule we're talking about, and we know exactly what type of a transition is happening. So for example, this is for hydrogen, okay? So if I observe in my spectra 410.1 nanometer wavelength, then I know it's for hydrogen, and I also know what type of levels they're involved, level 5 to level 2. And these are usually available from quantum mechanics. So for example, here we have 410.1 nanometers. So there's a line here, there's an emission line, right? Because the rest of it are black, but then this is the only intensities that we can see. So there are some photons coming with this wavelength. And I know exactly this, there it is. So if I know what I'm talking about, I can identify the molecules that we're dealing with here. And the same is true for absorption. If the electron that exists here gain enough energy to go exactly to the level 5 where it was before, for example, then it absorbs a part of a electromagnetic wave and absorbs some energy to go up to be excited and go up to the higher energy levels. And that absorption has the same frequency of 410.1. Okay, so in other words, this is both true for absorption and emission. Let's take a look at these two animations that we have, one for the emission lines and the other one for the absorption lines. Let's take a look. So for the emission, what we're going to do is currently the electron is existing here at level 1. What I am going to do, I am going to apply some sort of an electric shock or a potential to this atom, and I'm going to excite it to a higher energy level. Once it's going excited to a higher energy level, and then it will cascade back to a lower energy level automatically. And you can see the photons are coming out. Let's do that. So what happened was it went all the way to 5, and then to 2, and then to 1. One more time. Something else, to 2, to 1. So you can kind of see that it's emitting photon, and as it's going from a higher energy level to a lower energy level. So I was 5 to 1. So as it's happening, you can see that the emission lines are there. For example, for 5 to 3, we have something, and from 3 to 2, we have something else. The same is true for absorption features, right? If I have a gas cloud here, then I can easily say that some of it is being absorbed and reflected by the gas cloud. So that's why there are these dips in intensity, okay? If we change our direction of the telescope, so we're not directly absorbing or observing so this is the direct observation, this is indirect observation. We can kind of see that there are some emission lines that are coming out of this cloud because it's reflecting some of it. So that's why we don't see the continuum because we're not directly observing the star anymore, but we're looking at this gas cloud and we see these emission lines happening. This is enormously important because it can tell us a lot about these molecules that are inside a gas, an unknown gas. So for example, if I'm seeing something like this in my spectra, then I can for sure say that this is helium because I can make this in the lab and I can compare what I have in the lab with what I see in my observations. Sodium and neon and so on and so forth. So let's take a look at the composition of a mysterious gas. All right. So sample number one, so this is the sample, right? So this is the sample. And I wanted to know what type of a gas is inside. So this is the emission lines that I'm getting from a mysterious gas. But I can go in the lab and I can see if I can make these a spectra and I can compare. So I can easily turn on the hydrogen and see whether I have hydrogen inside. Apparently there are, whatever I was sampling using my telescope, there is a hydrogen inside that gas. So because there is one here, the emission line here, there's another emission line here, here, and here. Let's do helium. There's a helium involved. So you can turn all of these on and kind of compare. Is that what you're getting? No. So you can play with these and kind of guess the um, composition of the mysterious gas that you're dealing with in the sky. So that's why they're chemical fingerprints, because all of these molecules are individual. They're very unique. So if I'm looking at the hydrogen lines here, then I would be able to easily say that there's hydrogen inside my gas that I'm observing. Or helium, or oxygen, or other things. So these are indeed chemical fingerprints. They are very unique for each atom. Let's take a look at the solar spectrum. So thought question, and again, I want you to go ahead, pause the video as I'm reading through these thought questions, answer them, and then play the video. So which letter or letters labels absorption lines here? So which part of the spectrum the intensity drops? Okay, C and D, that's where the absorption features are at. Which letters labels the peak greatest intensity of infrared light? Infrared light. So this is where, so because this arrow is showing on where infrared is going to, so the answer is E. Which letters labels emission lines? So we're talking about spikes in intensity where intensity goes up. The answer is A. Okay, so these are few features that we usually see when we're looking at our spectra. How does light tell us the temperature of the planets and the stars? We obviously know a lot about the temperature of these features that are available to study, but we've never been there. For example, we've never been to the sun, and we know exactly what the effective temperature of the surface of the sun is, like 6,500 something. So it really is, it goes back to this study of its light, okay, and can tell us a lot about these stuff. So nearly all large and dense objects emit thermal radiation, including stars, planets, and even you. However, the difference is you don't have enough energy to create it all wavelength. So you don't you only emit in the specific part of the wavelength. For example, our body emits in the near infrared. So all objects' thermal radiation spectra depends on only one property, and that is temperature. So here you can see that a K-type star, a 3000 K star, K, which is a M-type star, low, temperature, it emits in almost a huge portion of a wavelength. Not obviously everything, but it shows that there's a continuum spectra here. Your body, on the other hand, is only 310 degrees Kelvin. So you're only emitting in a specific part of the wavelength, and obviously not every part, and it's only in very low intensity. That's at the near infrared. If you go to a 5,000 K, star, something like our sun, you're emitting in everything, and you peak somewhere here, which for our sun is here in the visible part. And then if you go all the way to a O-type star or the blue-type stars, which are 15,000 K effective surface temperature, then you can see that it is creating a huge intensity. And the intensity is increased in all portions of the electromagnetic wavelength. Okay? This is called Wayne's law. So here, go back to the little video that I was supposed to show you here. So let's say that I have the temperature, and I can change the temperature as I go from a very low temperature, okay, so 50 K, all the way to a very high temperature, okay, which is 100,000 K. You can see that the intensity of the light changes in a different portion of the electromagnetic wavelength. And the hotter the object is, it emits in every portion of the electromagnetic wavelength in a higher energy, in a higher intensity. Okay, so not only covers more area of the electromagnetic wavelength, but it's also emitting in everything in a higher intensity. Okay, so if I go here, you're probably missing some ultraviolet here, but if I go here, not only you're covering that, but you're also going to a higher density everywhere else, if that makes sense. So thought question. Which one is hottest? A blue star, a red star, a planet that emits only infrared light? Blue star is hotter because it's covering more intensity in the blue portion of the spectrum. And so when we study its spectra, we can kind of know what we're dealing with. Why don't we glow in the dark? That's a very silly question, but it's also very important. So pause the video, read these answers, and so try to guess the best. So people only emit light that is invisible to our eyes, which is in the near infrared. So if you walk into some of the buildings, they have a near infrared camera. Army use near infrared camera. It has a huge usage because you can go and hide in the dark, but you cannot avoid the emission of the infrared from your body. So our body is cold, about 310 Kelvin, so it's the perfect temperature for emitting in a near infrared. So let's talk about this specific spectra, interpreting an actual spectra. So what I showed you before at the beginning of this chapter was an actual spectra of an object. So by carefully studying the features in the spectrum, we can learn a great deal about the object that being created. So here, let's take a look. So we have reflected sunlight here, right? This looks like a solar spectrum. So whatever it is, it's reflecting sunlight. So continuous spectrum of visible light is like sun. Expect that some of the blue light has been absorbed. So whatever that object is, it should be red. And so we have some thermal radiation here towards the infrared, right? Thermal radiation peaks about the wavelengths corresponding to the temperature of about 225 K. So it's a cold object, even colder than our bodies. So here we have carbon dioxide absorption features. So the carbon dioxide or CO2 absorption lines are happening right here, which means that atmosphere, whatever it is, in its atmosphere, it has CO2. Then we have some emission features here, which are happening in the ultraviolet part of the spectra. So indicated in the hotter upper atmosphere. That's what it means. That object is Mars. So what you were looking at throughout this lecture so far was the spectra of Mars. So and that's how we identify things. We're looking at them. We're looking at the spectra. We identify their temperature. Well, we identify the features that we see. For example, when we see this and we say, oh, there's a CO2, we obviously have been you know, sending different things to study Mars, but you know, we can learn a great deal of things about when we study the spectra of these objects. Okay, so I'm going to stop here for the end of part 2, and we'll continue with part 3, right? Stay tuned.